All right, let's get right into it. If you've ever laid out a circuit board, I bet you've heard this piece of advice. To keep your signals clean, you have to split your analog and digital ground planes. Well, today we're going to tear that idea apart because that common wisdom, it might just be the very thing causing all your noise problems. Yeah, this is the big one, right? This is the fundamental challenge every single one of us faces with mixed signal designs. You've got these super fast, noisy digital circuits on one side, and then you've got these really delicate, high-precision analog parts on the other that need total peace and quiet to do their job. So how in the world do you get them to play nicely together on the same board? So here's our game plan. We're going to start by really defining the challenge. Then, we'll dive right into busting that common myth about splitting ground planes by showing you the problems it actually creates. After that, I'll walk you through the much better solution, and we'll wrap it all up with a super practical checklist you can literally use on your next design. At its core, the problem is really a clash of two different worlds. Your digital circuits, with their crazy fast switching edges, are just inherently noisy. I mean, they're practically screaming high-frequency energy all over the place. And then you've got your analog circuits, which are the total opposite. They need a rock-solid, quiet-as-a-mouse reference plane to make any kind of accurate measurement. So here's the thing you absolutely have to get right. It is all about managing where the current flows. Specifically, we're talking about the return current. See, every signal that goes out has to find a path back home, and our number one goal is to make absolutely sure the return path for those noisy digital signals doesn't take a wrong turn and wander into the quiet analog neighborhood. And this brings us to that classic piece of advice, the one that seems so intuitive. If you want to keep two things separate, what do? You build a wall between them, right? Well, in the world of PCBs, that means taking a knife to your ground plane and physically splitting it into an analog side and a digital side. Makes sense on the surface, doesn't it? In this picture, this illustrates the problem perfectly. We've got our signal trace, and it just hops right over that split like it's not even there. The signal gets across, no problem. But wait a minute, what about its return current? It has to get back to where it started, and it sure as heck can't jump across that giant canyon we just created. And right there, with that one simple question, the whole split plane idea starts to fall apart. By trying to solve one problem, keeping the ground separate, we've accidentally created a much bigger and more destructive problem that has everything to do with the physics of how current actually wants to flow. Okay, so here's a little bit of physics, but stick with me because this is absolutely crucial. At DC, low frequencies, current is lazy. It takes the easiest road, the path of least resistance. But at the high frequencies we're dealing with in modern digital logic, the rules change. Current follows the path of least inductance, and what that really means is it wants to form the smallest possible loop. This graph just nails it. See that big peak in the center? That's our signal trace. That curve shows you where the return current is flowing in the ground plane right below it. And as you can see, almost all of that return current is packed in super tight, right underneath the signal. It wants to stay as close as it possibly can to its buddy, the outgoing signal. And if you need numbers to prove it, here you go. Look at this. Within a distance of just 5 times the height of a trace off the plane, you've already got almost 90% of the return current. By the time you're out to 10, it's 97%. This isn't just a gentle suggestion from Mother Nature, it's a powerful force. The signal and its return path are a tightly coupled pair. So let's go back to our split plane. When we run a trace over that split, we are forcibly breaking up that tightly coupled pair. The signal gets across, but the return current slams into a dead end. It can't cross. So it has no choice but to take this massive, long detour all the way around to find the one spot where the planes are connected. And that detour is a complete disaster. A nice, small, tight loop gives you low inductance and very little electromagnetic radiation. You get a clean signal. But forcing that current to take that huge detour, you create a massive loop. And a massive loop is just another name for a very efficient antenna. It radiates noise everywhere, wrecks your signal integrity. You've basically just turned your nice, quiet PCB into a noisy radio transmitter. Not good. Let's just look at this side by side. On the left, that's the nightmare scenario. A trace crossing the split, creating that giant noisy current loop. Now the image on the right shows a workaround. If you absolutely have to have a split, you can create a tiny little bridge right under the trace. This keeps the return path small. But man, it requires incredible discipline, and it's easy to get wrong. So, if splitting the plane is so risky, what's the better way? Well, the answer is elegant. It's not to split the copper, but to split the function. We call this partitioning, and it works beautifully with a single, solid, unified ground plane. Okay, now this is what a good layout looks like. First thing to notice, there are no splits in the ground plane. It's one solid sheet of copper. The real magic here is in the component placement. We've grouped all the digital parts together in one area and all the analog parts together in another. Think of it like a digital city and an analog town living on the same continent. And here's why it works so well. Remember how those high-frequency return currents want to flow directly under their traces? Well, if you keep all your digital traces routed only within the digital city, the return currents will naturally stay there too. They have absolutely no reason to go on an adventure over to the quiet analog town and cause any trouble. The solid ground plane gives them exactly what they want, the shortest, most direct path home. All right, so let's boil all of this down into a simple, actionable set of rules. A checklist you can use to make sure your next mixed signal design is clean, quiet, and successful. Okay, here it is. Number 1, partition your board. Think about your floor plan before you route a single trace. Second, use one solid ground plane, no splits. Then, be super strict with your routing. Keep digital traces in the digital area and analog traces in the analog area. And this is the big one. Never, ever route a digital trace over the part of the ground plane that's underneath your analog section. Don't cross the streams. Routing discipline is everything. And that's really the big takeaway here. The secret to a great mixed signal layout isn't about chopping up your copper with crude splits. It's about being smart, partitioning your layout intelligently, and having the discipline to keep your signals where they belong. If you do that, you'll let physics work for you, not against you.